0.05. Oh, come on. Oops, wrong way. All right, you had 99%, and this was a proportion, so you had Z star, which would be 2.58 for 99%. It did not give you a p-value, a p-hat, so you had to use what? 0.5. 0.5. And you wanted to know what the sample size needed to be, right? All right, so if you work this thing out, divide by 2.58, square it, multiply, what you get is the n multiplies over to this side, so it ends up being reading greater than or equal to. You see where you made your mistake? So we're going to divide both sides by 2.58. This is making me crazy. It's acting up. I'm going to square this, so that goes away. And then we have to cross multiply the n over here. So we have 0.05 squared, 2.58 squared, n over here. And then we have 0.5 times 0.5 is 0.25, right? So you see why it has to read greater than or equal to? Because your n went to the other side. And we know n has got to be positive, so it doesn't change the sign. So what you get is n greater than or equal to like 665 is what you guys said?
Yeah, something like that.
Or 658, whatever you got, 600 and something, right? Well, what's the next number bigger than that number?
I didn't know where to go with 658.
All right, well, you had to read this. N has to be bigger than. Because remember what it says. What is the smallest number of consumers? Well, of the choices you had, anything from 650 or below did not fit the criteria, did it? All right. So that's why. Did that explain your question?
I think I just
Calculated wrong?
wrong.
Okay. All right, 6 was A. 6 was A. Inference was violate, good. 6 was A. 7 was D. If you went to a 95% confident, the interval had to get bigger, right? For the interval to get bigger, your plus or minus, your margin of error had to be bigger. Make sense? 8 was C. The next number bigger than 605 would again be 608. If you got 605 and then you didn't know where to go with that, just like the last one, it's the n goes to the side where it makes it bigger than. 9 was E. And 10 was D.
What was 8? D.
8 was C. 608.
I got 609.
The next biggest number, you should have gotten about 605 when you solved it, but it would be n greater than or equal to 605, and the next number bigger than 605 was 608. All right, so 10 was D. Free response?
Oh, we panicked.
Yes, you should have panicked. In A, P is the true mean proportion of visitors who favor vehicle restrictions in Yellowstone. You are doing a one-prop Z test, or one-prop Z int. Your conditions, random. In quotations, ask a random sample of 150 visitors. Independent, it is reasonable to assume more than 1,500 visitors to Yellowstone. And normal, you had to do the large counts condition, right? So 150 times 89 over 150 is 89, which is greater than 10. And 150 times 61 over 150 is greater than 10. So we can assume it's approximately normal. Once we did that, we run our actual confidence interval. You get plugging in 0.593 plus or minus 2.58 should be your Z star times the square root of 0.593 times 1 minus 0.593 divided by 150. That gave you a confidence interval, if you ran it on the calculator, of 0.49 to 0.70. So we are 99% confident that the true proportion of visitors who favor vehicle restrictions in Yellowstone is contained in the interval 0.49 to 0.70 inclusive percent. That should be 0.49 to 0.670, or you could have written 49 to 70% inclusive. Part B. More than half the visitors to Yellowstone Park in favor of the proposal? I would say yes. You conclude that? Yes, because 0.5 is well within the interval. As a matter of fact, it's very much within the interval. In stuff above 0.5 is in the interval, right? As a matter of fact, quite a bit, all the way to 70%. From 50 to 70% is in there. Therefore, it is reasonable to assume that more than half the visitors, that P could be more than 50%. Again, it comes down to within the interval. Number 2. It said to, is the normal condition met? Well,
You tell us.
Well, N is 48, so yes, 48 is bigger than 30, so CLT is satisfied. So A is yes, because the central limit theorem is satisfied. Part B says explain why the interval is wrong. Well, number 1, 1.96 is your Z star, not your T star, right? And number 2, 0.372 degrees of freedom. 47, by the way, the square root of 47 is wrong. It should be square root of 48, right? They put the degrees of freedom in there and not the other. Okay? And they told you the standard deviation was 2.576. And they put 0.372. There was everything wrong with that thing except for 6.208. Give the correct interval. The correct interval should have been from 5.46 to about 6.96. Don't forget to go back and double check. This is a good practice for you for the test. Don't forget to double check your answers. By the way, starting next time, you're going to start to get warm-ups that have to do with other sections. Since we're going to be down to the wire and getting everything covered, I want you to be able to have some time to review stuff for the test. So,
Stop. I've been sad.
What do we do then? Walker's been sad.
Walker has been sad.
celebrate, go to college, party, have fun,
What do we celebrate?
I don't party. I'm not
grow up, get a job, pay taxes,
What are taxes?
have kids, get married, hopefully not in that order.
I don't want to do that.
All right, number 3.
Have kids, get married, not in that order. Already at 3.
Number 3, you needed to panic. Number 3, mu is the true mean number of bacteria per milliliter in raw milk received by the factory. You are running a 1 sample T-int. Your conditions, you know that random sample of 10 1 millimeter specimens of milk. That's your random. It is reasonable to assume there are at least 100 samples of milk that can be made from the 100 shipments, right? And you could not check for CLT, so you had to draw the box plot. In the box plot, you should have noticed that it was relatively
Normal.
symmetric with no obvious outliers or skew, so we can assume it is relatively normal. We run our 1 sample T-int, and we get an X bar of 4,950, an S sub X of 268.5 or 45. We get a T star of 1.833. So we get 4,950 plus or minus 1.833 times 268.45 over the square root of 10. That would be your work shown to get the interval of 4,794.4 to 5,105.6. We are 90% confidence the interval from 4,794.4 to 5,105.6 bacteria per milliliter contains the true mean number of bacteria per milliliter in raw milk received at the factory.
What do they consider
I
fluoride?
don't know everything.
Straight up the D.
All right, next set.
Oh, then we're back to
One was A. I'm sorry, no, one was B. Excuse me, B.
twice.
One was B. Oh, wait a minute, hold on. One is A. Excuse me. One is just like the rest of them. One is A.
What is
One is A. It had to be greater than or equal to
I think C.
385. Right? Because the n goes over. All right. And the next number bigger than 322 is 385. Because it was 322.7. All right. 2 was B. 3 was C. C was the one that was false.
Is that who it was to?
2 was B. T star was 1.753.
I need one. I know it's correct.
4 was C. 4 was C.
So 5 is C. Yes.
5 was E. E. Again, just like the other ones, the next thing greater than. 6 was C.
Back on.
7 was A. Guys, come on. Narrowest confidence interval, smaller sample size, and the smallest level of confidence. Right? No. I beg your pardon. It's C.
Yeah.
7 is C. I just thought that out. C. Sample size gets bigger. It gets smaller, narrower, right?
Yeah.
Okay.
Yes.
Narrowest interval.
I have cash right now if I can pay you.
Yes. Go for it.
There you go. Thank you.
Thank you.
The only reason I might not fail is 5 points. You're not getting 5 points. Still need that. Choosing 5, joking.
All right. 7 was C. 8 was E. E. You don't know what percent it increases it by.
Miss Duffy, all I'm saying is if I can get those points, I'm going to have to rearrange my teachers on my Star Senior form.
Wait, why is that a thing? Is it like
9 is C. Yeah, kind of. No, it's who, not necessarily who's your favorite. It's just who would you want to give it to
Who
you.
you want to present
Yeah.
the award if you get it. So
I get to present one every year. I'm so excited.
That's your favorites.
Usually every year I get to present one. So I love
I
that.
think Miss Maya has like all 30 here now.
Miss Duffy, who has the forms? Because I
Miss
lost
Maya.
mine.
I think Miss Maya. I don't know. I don't have it. All right, guys. 1 free response. You had to panic. N was 1,026 and X was 400. X bar was 400, right? Well, X was 400. Do you know how I got that? 39% of 1,026, right?
You said it was what?
Okay. 400. It was 400 point something, but you can't have point something. P is the true proportion of U.S. adults who would respond, make some major changes to the question. What would you like Congress and the President to do during the next year? P hat was 0.39. You're doing a 1 prop Z int. Random, in quotations, random sample of 1,026 adults. Independent, it is reasonable to assume at least 10,260 adults in the U.S. And normal, you had to do the large counts. So you got 1,026 1026 times 0.39 would be greater than or equal to 10, and 1026 times 0.61 would be greater than or equal to 10, right? So can assume it's approximately normal by the large counts. It said, well, you had to find the confidence interval. Find a 95% confidence interval for the proportion. Then give an interpretation of the confidence interval and the confidence level. So the first find tells you to panic. If you have to construct the confidence interval, you ought to be panicking. All right. So you got a z-star of 1.96, which means your confidence interval should have been 0.39 plus or minus 1.96 times the square root of 0.39 times 0.61 divided by 1026. You should have gotten the interval off your calculator of 0.36 to 0.42. We are 95% confidence that the true proportion of U.S. adults who would respond, make some major changes to the question, what would you like Congress and the President to do during the next year, is contained within the interval 0.36 to 0.42%. 95% confidence means for repeated samples of size 1026 from the same population, approximately 95% of the confidence intervals will contain the true proportion. It asked you to interpret the confidence level.
Didn't say that.
You got to answer all of it. Yeah, what brought you down? Number 2, part A. Create the confidence interval, so you had to panic. Mu is the true mean amount of time a pen can go in hours before it runs out of ink. Random, a random sample of 49 pens. Independent, it's reasonable to assume there are more than 490 pens produced by the company. Normal, N is 49, which is greater than 30, so we can assume approximately normal by CLT. N, it is a one sample T interval. The interval, T star, is 2.011. So your interval was 188 plus or minus 2.011 times 6 divided by the square root of 49. You should have gotten an interval of 186.3 to 189.7 hours, right? So we are 95% confident that the true mean time in hours as an ink pen produced by the company can go before it runs out of ink is contained in the interval 186.3 to 189.7 minutes, or hours. Part B, he claims that this means they will operate 190 hours. That is not true. 190 hours is slightly above the top end of the time interval. So it would be considered unusually long amount of time for the pen to last, wouldn't it?
Yeah.
Remember that for today. And part C, what's the probability that another random sample of 49 pens will have an average 190 hours or more? It'd be less than 2.5%, because less than 2.5% of the intervals contained something other than the true mean, right? So it would have to be one of those 2.5%. Now, why did I say 2.5%, not 5? Because each side gets 2.5. Yes.
I thought we were looking for like a specific.
No. Well, I mean, there is an exact percent. It's 2.5%, because you have 2.5% chance of the interval not containing the true mean. Now, make sure when you answer that question, you answer it as an interval. You have to include that 2.5% is the probability that the interval will not contain the true mean. All right. So let's talk notes today. You have a test next time on this information on Friday. So let's talk about this. Now, this is going to bring around, I was telling everybody, this brings back our Parkinson's people. Do you remember at the very first part of class, when we first started, we talked about this Parkinson's case, didn't we?
The one where she could smell the bug?
She could smell the Parkinson's. What did we decide? Do you remember what we decided was really proof that you could actually, what was considered reasonable proof?
100%.
Close to 100%, right?
Yeah.
We said we wouldn't believe we could, so 11 or 12, right? So now, if you're just guessing, let's look at number 1. Let's remember probability. This is in your notes, day 1, in your new packet. It says, suppose Joy is just guessing as to whether each shirt belongs to a Parkinson patient or not. How many out of 12 would you expect her to guess? Out of 12, how many would you expect her to guess correctly? No, not knowing she could smell it.
Yeah. 2.
Half. 50-50. Yes or no, right? So what would be half of 12?
6.
So we would expect maybe 6, right? How many would it take you to convince you that she could detect it?
12.
About 12. We would want to say 11 or 12, right? But really 12, because we would expect her, we would need true proof. And any one of them being wrong would indicate there's some flaw in her ability, isn't there? So explain our choice. All corrected, there'd be some doubt. Now we did the simulation at the time. Remember we did it, clicked it on the, drew the cards, guessed, lucky guessers. We're gonna not go back over that. And if I remember correctly, a lot of you guys got 6. 6 was right in the middle, wasn't it? About 50%. Yeah, nobody got 11 or 12 though. All right. So now, this is for when we did it in class last year. Just so you know, I'm going to give you some data. So when we did this in class last year, this is what we got. We had one person guess 2.
Should we copy this?
Yeah. This is what we got, because I had 6 people in class that day. 6 people in class, yeah. This is what we got. Yep. Even with just those 6 people, this is what we got for our answer. It is very small, but it still turned out okay. This box plot would be all right, wouldn't it, though? Take a look at what the curve would look like. It's not very skew, is it? It's pretty symmetrical. And it's actually right where we think the peak is, right where we think it should be, isn't it? Yeah. All right, so using the simulation results, calculate the probability of correctly identifying each of the following. At least 8 shirts.
1/3.
No.
1/3.
Looking at this, it says.
Yeah.
What is the probability?
1/3.
Yeah. 2 out of
6. 1/8.
at least 11 shirts.
0.
At least 10 shirts.
0.
At least 12 shirts.
0. Well, would you put it out of 6 or out of 12?
Oh, at a 6. I don't know why I put 12. 6.
You crazy.
6. 6. I don't know why I did 12. All right. Do these probabilities affect your answer to the second question? No. As a matter of fact, it shows it's very what? Unlikely to guess ten, 11, or 12 shirts correctly, doesn't it? And it's really unlikely to get 12. We've already done the woman who, we all did all that stuff, right? So now, this is what we're talking about. This is the emphasis for the rest of this class. From now until you take the exam, this is our emphasis. How rare is too rare to simply be by chance?
0. So are we taking a test right now? This is Friday. Friday.
Yeah.
Oh, okay.
You've got Unit 8, Unit 9, Unit 10, and Unit 11.
So 8 more tests. 8 more tests. Well, she usually splits them up.
Unit 8, Unit 9, Unit 10, and we probably won't test on Unit 11. We'll just go over that in material because it's very short.
That's what we took. Yeah, but then you said she said units.
All right.
That's what you
Only once. Unit 5, because probability is so big. All right. A hypothesis test is also referred to as a significance test. Okay? Now, guys, significance test, it means how significant are the results? That's why we call it a significance test. Are the results significant enough? In other words, what level of error are we willing to accept, if you want to think about it that way? Okay? Well, usually we're willing to accept a certain amount of question. How much depends on what the question is. In normal studies, guys, if you remember back to when we were talking about experiments, usually we talked about this a little bit there. If we're doing an experiment that's just a regular old statistical experiment and it doesn't involve drugs, we're willing to accept about 5% error, right? Think about it. 2.5% on either end or 5% on one end. 5% error, we're willing to say, okay, if it's up here, it's really unusual, which means our hypothesis is not proven. If it's within this range right here, we consider that if it's a normal curve, that it's within about 2.5, 3 standard deviations, right? 2 standard deviations, we consider that pretty not unusual. Anything above that or below it is unusual. Okay? Now, for drug tests, however, we don't accept 5%. We accept 1%, which is like 0.5% on either end. Think about why that is. If you're doing a drug test and you want to make sure that drug works, you don't want 5% question, do you? No. That can lead to a lot of bad things in lawsuits.
That'd be like a Germex bottle saying works 90% of the time.
Yeah. Now, procedures. Okay, so a hypothesis test, referred to as a significance test, is a formal statistical procedure that uses observed data to assess the truth about a parameter value. And what are my parameters? Mu, sigma, and rho. Rho? Mu and p and sigma. Sigma is standard deviation. All right. Is there convincing evidence? These are the phrases that you're going to get on the test. They're not going to tell you to do an inference test. Okay. They are going to give you phrases like, is there convincing evidence? No. Is there statistical evidence? Does the data provide convincing statistical evidence? We are going to run what we call, instead of panic, we're going to run phantom. Now, some of the things still mean the same thing. P is what? Parameter. Still parameter. A is still our assumptions. N is still naming the test. And you're going to have to get the other ones. So let's go through these and figure out what they are. We begin, as with confidence intervals, by defining the parameter. Every hypothesis test, God, it's hard to say, has 2 hypotheses.
Why 2?
Because you've got the one that you're hoping is the truth and then the alternative.
The null hypothesis.
Yes. If you've had AP Bio, you recognize this. We have H naught, which is known as the null, and HA, which is known as the alternative hypothesis. H naught is the parameter value equals the claim value. H naught is always equals. HA is any other value. If it's not equal to, ho and ha is really what we call them. I do. You'll hear me say ho and ha. If the P is low, reject the ho. You will remember that phrase. She got that from me because that's what I use. Ha is the alternative hypothesis, and if it's not equal, what are the other possibilities? Less than, not equal to, or greater than.
What about
Now.
less than equal to, greater than equal to? Could you?
No.
That made it.
Less than, greater than, or not equal to. Can include equal to. Now, for less than or for greater than, this is a one tail. I want you to think about why this is one tail. Less than would look like this. We'd have this line right here, and it would be here.
Yeah.
Greater than would
You're
be
looking at one side.
Yeah.
one side. But for not equal to, we have both two-tailed, which is both possibilities. Not equal to means it could be either of these ends. So do you see why we call it a one-tail or a two-tailed test? That makes a difference when you're running your percent. Because if it's a one-tail, then the percentage is all on one end. If it's a two-tail, we have to split. We have to split it, don't we? Are we good so far? Okay, so let's run. Did everybody get that, or do I need to go back? Are you good? Y'all good? Okay. So now it says define the parameter and write a pair of hypotheses.
Words. There's like no math left.
There's math.
Where?
It's just calculator math.
It says 16.
Can I go to calculus?
Sure, I'll let Miss
So serious.
Haddock know you'll be there
I
tomorrow.
don't know what
Gladly do.
No, you're going to pass my AP stats exam
I
and
am
give me good
not.
numbers. Yes, you
I
are.
will bet so much money that I
You
won't.
will.
If you don't, you're ugly forever.
I already am. Because Duffy said so.
Never said you were ugly.
Yes, you did.
No, I didn't.
We read between the lines. We knew what you were trying to say.
At worst, I said your girlfriend is prettier than you, but that does not imply that you are ugly.
It means I'm not pretty.
No, it doesn't. It just means she's prettier.
Then ugly.
You don't have to say it.
Y'all.
What? That you're ugly?
Yeah.
I'm not saying it. Just Duffy is. You just
Shut
said
up,
it
Riley.
again.
This is a hypothesis.
Walker's ugly.
No, Walker's girlfriend is pretty does not imply in any way that Walker is ugly.
No, that's not the way you said it.
That's not the way you said it.
Your hypothesis was your girlfriend's only winning you for the money because you're clearly ugly. That was your hypothesis.
What?
No, it wasn't. That's what you
No,
said.
no, that's what you said.
Now,
You were saying that the other day when Walker was in the bathroom.
I did not. You're lying now. I'm going to take 5 points off your test. Give them to him.
No.
Keep talking.
Keep talking, please.
In a New York deli that makes very large sandwiches, that would be most New York delis, a typical sandwich is supposed to have 16 ounces of meat on it, or 1 pound, right? The sandwich maker never weighs the meat and just puts it on by eye. The manager of the restaurant is concerned that the sandwich guy is putting too much meat on the sandwich. So we want to first do mu. Why mu?
Because
We have mean.
yeah, that is the average.
Yes.
What it's supposed to be.
A typical sandwich is supposed to have that much. Never says average, does it?
No.
Never, but there's no percent.
Well.
If there is a percent, if this is a percentage, a proportion, there will be a percentage included. This has no percent, so it is therefore going to be a mean. What is the true mean?
16 ounces.
No. We're defining mu. The true mean what?
Amount of meat.
Oh.
Amount, yes. Amount of deli meat. In what, Emma?
OZs.
In ounces. That's what? Placed on a sandwich.
I could go for the means.
Now we need H naught is mu equals what? What do we assume the truth is going to be? What are we testing? Whether or not it's what?
Exact.
Exactly 16 ounces. And HA is mu is what?
What does that say? Oh, 16 ounces. I thought it said 1 log.
Does not equal 16?
Read the prompt again. Read the last line of the prompt.
So I'd be greater than?
He is concerned that the sandwich guy is putting too much meat on the sandwich, so it would be greater than 16 ounces. I guarantee he's not upset if they're not putting enough on. That would be H naught, that would be HA. Now, look at part B.
Okay, that's not too hard.
A cancer research group estimates that 28% of women who are more than 40 years old have yearly mammograms. For this, all it said was define the parameter and write a pair of hypotheses. We'll get into the other in just a minute. Cancer research group, 28% of women who are more than 40 years old. Let me just put it this way. If you can't write the hypotheses and the alternative, you're sunk from the get-go. Many insurance companies are changing their coverage for such preventative tests as mammograms, which may impact the proportion of women in this age group who have yearly mammograms. So, what is P? Define it.
0.28.
No.
It is the percent of women.
The true proportion of women, what?
Who get greater than 40 mammograms who have yearly mammograms.
More than 40 years old.
Aren't people above, like women above 40, not supposed to get mammograms or something?
No, we're supposed to get more of them.
More of them? Oh.
We're supposed to have, you hit 50, they want you to have one every year.
Are you a 40-year-old woman?
Well, no, but I heard
Then you don't know what you're
from
talking
someone
about.
at the hospital today that a 40-year-old woman and up are supposed to get them. So they're obviously wrong.
Mammograms?
Yeah.
The older you get, the more likely you are to get breast cancer.
They said that after you're 40, you're not supposed to get them. So they're obviously wrong, I guess.
Yeah, I did hear something. I'm not.
I heard.
I am not.
No.
I don't know why, but
All right.
I do have.
What is H naught? Now, unless they've changed something on me and I don't know about it, I'd be thrilled not to have a mammogram every year. Those things hurt.
Not really.
They do. Do you know what they do in a mammogram to a woman?
I didn't even know what a mammogram
Okay, so they take your boob and they stick it between these two plates because they got to take an image of it. And these two plates slowly go together until they're about this far apart. So it takes something like this and turns it into a flat pancake.
we should do it.
And they take a picture so they can get all of the tissue pictured so they can see any lumps and stuff. Yeah, it is not pleasant. It's not the worst thing in the world.
Can I get a mammogram on my stomach?
Not the worst thing in the world, but what's really bad is when they come back to you and they say, we need to get another picture. And then you're like, oh, awesome. Let's play flat boob again. No, it sucks. All right, so what is H naught? Mu? Mu?
No, it's
P. P. Not P hat. P is equal to what?
28%.
0.28. HA. P is what?
Less. Greater.
May impact the proportion of women. Does it indicate more or less?
So it could be either.
Not equal to.
She's calling it, but
Yeah, that's what you're acting like.
okay.
Now,
Hey, Miss Duffy, I gotta go.
okay.
Where are you going?
We're practicing.
No, you're not.
P-value.
He's gonna go put
Back. Are you gonna be alone?
All right. So, what is the p-value? The p-value is what we're going to judge whether or not we are actually accepting this or, well, we never accept. We reject or we fail to reject. Okay? We never accept anything. So we're going to either reject or fail to reject. Now, if we reject, you've got to understand what p-value is. Remember, we've set this arbitrary based on some percentage we want, right? We've set this value of anything out here is considered unusual, right? If we get a value of P, think of P as the area under the curve, so to speak, where it's at. It's like almost like having a z-score. If the P is out here, if my p-value is out here, we consider that unusual, don't we? If we have an unusual value, that does not support our hypothesis. Our hypothesis area, this would be the H naught is acceptable area. In other words, we fail to reject it. If our H naught, if our p-value ends up out here somewhere in this shaded area, it's considered unusual, which means we would reject the p-value being what we said is the truth. Does that make sense to everybody? This sort of ties into confidence intervals, doesn't it? The true proportion should be here somewhere. If we find the true proportion to be out here, that means we're not very confident in that it being in here, are we? If we're not very confident in that, then we are rejecting this being the right interval, so to speak. Does that make sense to everybody? Tying it in? Okay, so if the p-value is way out there, the p-value, and the reason we call it p-value is the probability. The p-value is the probability and we're going to assume it's true. We're going to assuming H naught is true, because that's what we said H naught was, right? The probability, assuming H naught is true, of getting getting a statistic. Our statistic would be our X bar, our P hat, right? As extreme, or more so, as the observed statistic simply by chance. All right, let's read this and tie it into what I just said. So finish writing it down and then let's talk about this. Remember, the stuff underneath the probability curve, the normal curve is probability, isn't it? So if we assume H naught is true, for us to reject H naught, it would have to be outside, in other words, in that little area up there, wouldn't it? This is a p-value that is as extreme or more extreme because it's there or greater than whatever this line of demarcation is that we've established. Do you get that? This p-value is normally 5%. So if we get a value out here that's bigger than 5%, in other words, we get this guy as bigger if we're down here, lower if it's on this end, less than 5%, right? Or if it's two-tailed, this would then become 2.5% on both ends, right? If it ended up in the 2.5% area, it's as extreme or more extreme than whatever this line is we've set as our arbitrary we failed to reject line. Anything in here we would fail to reject. Fail to reject means that H naught is true. Rejecting, we're now out here, aren't we? Unusual, extreme value, we are going to reject. Does that make sense? If the P is low, reject the ho. If the P is low, that puts it out here on the ends, doesn't it? If it's out here on the ends, that's where it's not true. Tying it into what we've learned about confidence intervals. Out here is bad, in here is where we expect the truth to be. Get it? That's why it says as extreme or more so than the observed statistic simply by chance. So we're assuming our observed statistic is in the middle right here, aren't we? So we're setting this line. If the p-value is this percentage or higher, or this percentage or lower, then we reject. All right, interpretation of the p-value. Assuming that H naught is true, a p-value is the probability that the statistic will be as extreme or more so than the one we observed in our data by chance alone. And yes, I did just make you rewrite this. I want you to think about it. This is the thing you need to remember. This is one of those phrases that you need to add to your note cards. to remember how to interpret a p-value. We assume that if it's in the middle somewhere, it's not by chance. Okay? Are we fixing to go to lunch?
A little bit.
Okay.
They just got.
Okay, they just got to lunch. All right, cool. So are we good so far? Does everybody understand this? So here we go. A basketball player claims to make 75% of his shots at the free throw line. A college scout who also happens to be a stats professor observes the athlete in a game where he makes 14 out of 24. Conducting a test using the hypothesis, so they've given us a hypothesis of P is 75% and an HA, which is less than 75%, right? Yields a p-value, so they've given us a p-value of 0.0297. So I want you to think about this curve. With this alternative hypothesis, what should this curve look like? Where should the line be? Lines what? This is what? Less than 0.75, right? Less than. This P is different than this P. P value is not P. This P is sort of like P hat, isn't it? It's not, you never put a hat on these though. They're always true, the true statistic. So we're looking at the probability, aren't we? What I need you to look at is the less than for the shading on this guy. If we're talking about less than, we're talking about down here somewhere, aren't we? Now, typically a p-value is 5%, isn't it? So we would assume that this is 0.05 line right here. Does that make sense to everybody? Where is our p-value? Is it above that line or below that line?
It's below.
Our p-value is down here somewhere, isn't it? 0.0297. So basically what you're asking yourself is this in the unusual region?
No.
Yes.
I don't think
If it's in that little shaded area, it's unusual, isn't it? Remember, this is the area, the shaded stuff past the line is considered not unusual. This is considered unusual in here. Does that make sense? Statistically speaking, it's unusual. So is this considered unusual? Yes. So let's interpret this value. We're going to assume, what is H naught?
he makes 75.
Okay, so we're going to assume that H naught equaling 75% of free throws made is true. The probability of him making what?
Less than
Making, well, he made 14 out of 24, right? So 14 out of 24 is what, 58%?
14 out of 24.
Yep.
That's 58.3.
Okay, so about 58%. Or fewer. Why did I include the phrase or fewer? Remember what we said? It says that extreme or more extreme, right?
Yeah.
So more extreme would be even smaller number, right? Would be what? By chance. Got to use that phrase by chance. Is.
0.02.
Okay, so that's a percentage, isn't it?
Oh, 29.
is 2.97%. That's what that p-value means. It means he has a 3% chance of only making 14 out of 24 free throws. Statistically speaking, if we run this as he usually makes 75%, he has a very low probability of only making 14 out of 24, doesn't he? He'd have to be having a really, really bad night. If he, on average, makes 75% of his shots, that means a lot of the time he makes more than that. So standard deviations wise, this is less than 3. This is more than 3 standard deviations below the mean, isn't it? So that makes it unusual. Does everybody understand this now? Kind of? Okay. You don't always have to interpret the p-value, and you don't know if you always have to use that exact phrase, but you need to be able to draw the picture. If you were trying to explain and interpret this value, you would literally be saying, it's an unusual amount, right? I had a p-value that's typically 5%, then 2.5% is, or 3% is in the unusual area. So it's very unusual. You could say it's very unusual for him to make it. As a matter of fact, there's only really a 3% chance that he will make something that low based on the hypothesis being true. So you can change up the phrasing a little bit if you want to, as long as you get the idea across that you understand what they're talking about. Now, the things you have to include, the fact that the probability of him making this many is that, right?
So do we reject the hypothesis?
Yes, you would reject that as true. If the P is low, we reject HO. If he really only made 14 out of 24, which is very unusual for him, supposedly if he makes 75% of his shots, we have to assume that he doesn't actually make 75% of his shots. It's actually something lower. See how it works? All right, good follow-up question. All right, typically what we use the p-value for is this. To make a decision at the end of a significance test, you just fed right into that perfectly. We're going to calculate the test statistic, and we're going to calculate the p-values and all that fun stuff, all right? Making a graph to represent a hypothesis test. We're going to look at this again, and you're going to see it looks just like what we've been doing. Making a decision for a hypothesis test. Every hypothesis test includes a cutoff for the p-value, okay? Which is known as the significance level. Get it? It's a significance test. And we call this alpha. Significance level is Greek letter alpha. And it is typically what percent? 5%. So we use 0.05 usually if it's not given. Now what if it gives me a different p-value? Use that. Otherwise we use 0.05. If our p-value is less than alpha, we reject. If the p is low, what do we do? Reject the hoe. It's an easy way to remember it because it sounds so awful. The p is low, reject the hoe, right?
What do you mean it sounds
If the p-value is low, if the probability of it happening by chance is very, very low, then we have to assume that our truth is not really the truth, right? So we reject it. Totally makes sense if you think about it. Think about why that is. A small p-value is evidence against H naught. It indicates that the observed data is highly unlikely to occur with a true H naught. Isn't that what we said with the basketball example? If he only really has like a 3% chance, probability of only making 14 out of 24, if it's true, and he actually does that, then it's probably the truth is not the truth. All right. So we always say we reject. If the p-value is greater than A, we never, ever accept. Take the accept out of your vocabulary. We reject or we fail to reject. Accepting is like saying it's the truth, the ultimate absolute truth. And is anything in statistics ever the ultimate absolute truth? No. Remember, we're shades of gray here, aren't we? So we fail to reject. If you ever put accept, you will automatically knock yourself right down to an I. Never accept. This is not the same as saying we accept. Do not accept. Take accept out of your vocabulary. Reject, fail to reject.
You either reject the hoe or you don't accept the hoe.
You can never accept.
If you reject, that's the same as not accepting the hoe.
But you can never accept the hoe.
Never accept the hoe. That is a great way to put it, to remember it.
Either reject her, but
You can reject her.
and you
Don't ever
definitely
accept
can
her.
accept her.
No.
Kick her to the curb.
Kick her to the curb or just walk right on by and fail to kick her to the curb. But never walk up and say, come on, ho.
This is the greatest class ever.
What'd you talk about in stats today, hoes?
Mama,
Hoes and haws.
Mama, Miss W said you gotta get today. She said
I have this recorded. Not true. I don't know if that's a good thing or a bad thing, actually. All right. Think of it this way. When the verdict is handed down by and this is a great one to think about it. In our legal system, you are innocent until proven guilty. Okay? Now, we do not actually say you're innocent, do we? We just say not guilty. Is there a reason for that? We can't prove you're innocent. Innocent means something very different than not guilty. Not guilty simply means we don't have the burden of proof. It doesn't necessarily mean you're innocent. Which is why, if you can show that you're innocent of a crime and you've been proven guilty, then you can sue the state and all kinds of other things for taking your life away from you. All right? We always say guilty, not guilty. You'll never hear a jury say innocent. And there is a reason for that. And it's this statistical idea of here of rejecting or failing to reject. Okay?
Yeah, Riley.
All right. So let's look at decisions. Here we go. Here's your when the P is low, reject the hoe. We always put the following. We say whatever the p-value is less than alpha. Therefore, we reject H naught. Thus, there is convincing evidence for, if we reject H naught, then what do we need to fall back on? Look, remember, you have H naught, right? And you have HA. If we reject H naught, what are we going to? So there must be convincing evidence that HA is what? Ever, right? If we fail to reject, notice we're going through H naught each time, aren't we? So we look at H naught first and then decide whether or not we need to go to HA. If we fail to reject H naught, are we marking out H naught? No, we're using it. So then this goes away, and we don't even consider it. You see what I'm saying? The progress of how we go through these is we consider H naught first. If we reject H naught, then we go on to HA. If we do not reject H naught, we stop there. And HA never even comes into play. Does that make sense?
So if we reject the first one, then we need the other one.
Yes. Then there is convincing evidence for the other one. If we fail to reject, there is not convincing evidence for HA. Notice we never, in the second part of this, I want you to notice in the second part of this, what's always referred to in the second part? HA, isn't it? HA, HA. So there is convincing evidence or there is. So the decision part always has to do with H naught. The convincing evidence part always has to do with HA. Does that make sense? So if we mark out H naught, we go on and there is convincing evidence for HA. If we circle H naught, we don't go on and there is not convincing evidence to move on to HA. Does that make sense to everybody?
Yeah.
Okay. This is the place where most people make mistakes. You'll get the p-value, you'll crank through the calculations, you'll get the p-value, you'll reject or fail to reject, and then you'll write the wrong conclusion because you'll base it on the second one. You won't on the first part, but on the second part you'll go, so there's convincing evidence for H naught. No, there isn't convincing evidence for HA. All right? The convincing evidence part always concerns HA, the alternative. We can either establish there's convincing evidence for HA or there's not for the alternative. And if there's not convincing evidence for the alternative, this has to do with the whole never accepting H naught. Get it? By writing about HA in the second part, that keeps us from saying we accept H naught. We're just saying there's not enough evidence to say it's not true. Get it? We're not saying you're innocent. We're just saying there's not enough evidence to show that you're guilty. See the very fine distinction between those two? All right. So let's look at the notes. All right. Today we're looking at, I know there's 5 of you here. Today we're looking at conditions, and then we're going to actually calculate figure out how to find that test statistic so that we can compare it and find the p-value, all right? So conditions. Look what we have for conditions. Random, independent, and normal. It's RIN again. Guys, do we even really need to go over this? Think about it. We know how to find RIN for a proportion and for a mean. It's the same methodology because confidence intervals have this relationship with inference, right? Think about it. The confidence interval's in the middle and the inference is kind of out at the ends, right? Or one end or the other. Because they have this relationship, it's still the same. We're still proving it's normal, so we've got a normal curve so we can identify where the unusual is, all right? Okay, so for independence, if we're sampling without replacement, the sample must be less than 10%, right, of the population, or if the data comes from an experiment. Guys, we keep writing this, and people still end up missing it on tests and on the AP test. What does it say? If the data comes from an experiment, do we need to do the 10% rule? No. No need for the 10% rule. What do we have to figure out, though? Individual experimental units are independent. In other words, if I pick 10 people, each person is independent of the other person, aren't they? Yeah, you can throw that away. You just throw it away. All right? I gave you your pass.
Yeah.
Okay.
Can you check the green now or later? Because you remember some.
Yeah, I'll check it later. I'll put it in Power School.
Just
Okay, I will. Bye. Have a good one. All right. Individual experiment units are independent of each other. So if you're doing shrimp, it's got to be you're pulling out one sample and then putting it back in and then dipping another one, etc. You're not like keep on dipping smaller and smaller and smaller amounts where they're not independent, right? Okay, so we understand how that goes. And normality. If we're dealing with a proportion, the normality is the large counts condition, isn't it? So NP is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Notice we are using what here? P naught instead of, it's just P, really. In confidence intervals, we use P hat, but here we're going to be using P naught. Okay? All right. Now, why are we using P naught instead of P hat? Why did we use P hat in confidence intervals? What does that say?
It's all we have.
Did we have P? No, we were trying to estimate P. We are in these inference types problems, we're going to have an idea of what P is, aren't we? And we're judging off of P something else's validity based on what we know P to be, right? Okay, so for confidence intervals, we're estimating P hat or P. For inference, we're already going to have an idea of what P is. So very different in that regard, aren't they? All right, so what's our acronym to figure out how to run a test? An inference test is phantom. Well, P stands for what do you suppose? Parameter. What do you suppose H stands for? What is the first thing we write? Hypothesis. Hypotheses, right? This is going to be ho and ha. What do you suppose A stands for? What do we need to check next? It's the A, same A as in panic. Assumptions. In other words, our conditions, right? RIN. Name. If we're doing a proportion, it is a one prop Z test. Now, TO goes together. T is for the test statistic. Okay? And O is for obtain the P value. Okay? Because we have to compare our P value, don't we? M stands for make a graph. And a decision. We have to make a decision based on our test statistics and our p-value and our graph, right? These are all going to have something that goes together. So look at an example here. It says Benford's law, also called the first digit law, is an observation about the frequency distribution of leading digits in many real-life sets of numerical data. This is real statistical junks, guys. The law states that in many naturally occurring collections of numbers, the leading significant digit is likely to be small. For example, in data sets that obey Benford's law, the number 1 appears as the leading significant digit about 30% of the time, while 9 appears as the leading significant digit only about 5% of the time. Suppose a random sample of 300 large companies' expense reports has only 72 expenses that begin with the digit 1. Check conditions. There's room on the next page. And carrying out a significance test for a population proportion to determine if the reports have fewer first digits of 1 than allowed by Benford's law. So we are going to go ahead and do all of our different steps here, okay? So we're going to see those. Now it says assumptions. So what are my assumptions going to be? R, I, N, right? So where is random covered? Look at the second paragraph. Yep. A random sample of 300 expense reports, right? I, independent. We can reasonably assume what? There are what? There are more than 3,000 expense reports, right? At a large company, right? That's probably true. And N. How do we check N? So the first thing we need to figure out is what is the percentage? What is Benford's law saying? The number 1 appears as the leading significant digit about how much? It's saying P is 0.30, isn't it? This is what we're going to be checking against. Do you see how you can find that? All right, so we need to check. N times P is what? Greater than 10. And N times 1 minus P greater than 10. So N is what? How many samples did we pull? So we're doing 300 times 0.3, which is what, 90? That is greater than 10, boom. All right, and then we're gonna do 300 times what? 0.7, which is 210. That's also greater than 10. So we can assume it is approximately normal by large counts, right? Okay. So now, how do we find a test statistic? Z is our test statistic, guys. I want you to think about why we would pick a Z. It's a Z score, isn't it? Remember what the picture looks like, okay? We're looking for a Z score. In other words, we're looking for a boundary line, aren't we? Or a portion that's shaded and where it compares to the boundary line. The p-value is our boundary line. Do you get that? The Z is the amount of shading above or below some particular Z value. We're going to check that against our, what? Well, let's look at this. Test statistic. What does it say up here? How do we find Z? It's how we've always found a Z score. It's what? Statistic minus parameter, right? We're going to take what we think it should be, subtract what we actually found, right? Or the other way around. What is it? Observed minus expected divided by the standard deviation. This is a Z score formula, isn't it? Please remember, this is a Z score. It really is just a Z score, isn't it? Well, the statistic is P hat. The parameter is P. And notice, though, that it says the standard deviation of the statistic. Okay. But notice what's used in here. The parameter value. Because it's what we know. Be careful with that, all right? This is a formula that is on your formula sheet. Okay? This is on your formula sheet. So now we want to obtain a p-value that corresponds to the area. If P is less than P naught, this would be my Z. It would be down here, wouldn't it? Negative Z. And less than means it would be everything shaded here. Would you agree? Okay. What if HA is greater than? Now, why do I know these have to be HA? Because what is HO? Always. Equal. Right? All right. So HA is P greater than P naught. So this would be positive Z here, and it would end up being everything shaded above, right? This is for a one-tail test. What if it's not equal to? Not equal to is a two-tail test, isn't it? So then we have negative Z and positive Z, and we're checking to see if it's, what's the probability of it being out here, aren't we? Isn't that what a p-value is? It's sort of like a probability. And that's two-tailed is only where we have not equal to, right?
What did you draw right there?
Where? Two-tailed? Mm. How's this? Better? Okay. So does everybody understand the shading here? Does everybody understand how we'd find these? Look what it is. Why did we prove normal?
Because of the approximate.
Yeah. Now I need to highlight something for you here. How do we find the area? Calculate the area of one end of the curve and do what?
Multiply by 2 because of shift tails.
Yeah. You're going to be very careful about that. That'll be the thing that you don't end up doing. All right, so let's actually get back to our exam now, though, between z-scores and significant levels and test statistics, etc. All right, well, let's see. Walk through this whole thing. It says, refer to the earlier problem regarding Benford's law. Calculate the test statistic and the p-value. To do that, we need to start with ho and ha. So what is HO? This is a proportion, so it's going to be what? P instead of mu, right? So what did Benford's law say the truth, we think the truth is? 30%, so 0.30. Then we're going to do ha, which is we think from our sample we thought it was what? Less than, because it said only 72%, right? So we're checking to see if our p-value is actually less than 0.30. So is this a one-tail or a two-tail? It is a one-tail. We also need to find p-hat, don't we? P-hat in this case was what? How many samples did we pull out of the 300 that had a 1 in front of them? So 72 out of 300, which ended up being what? 0.24. Okay? So let's get our test statistic. So our z-score that we think is going to be what? P-hat, right? Minus p divided by the standard deviation. P, 1 minus p over n. So let's find this. What was p-hat? So this is going to be 0.24 minus what? 0.30 divided by, and we're going to do the square root of 0.3 times 0.7 divided by what? Does everybody understand where the 0.3 and the 0.7 came from? So if you crank this through your calculator, you should get a z-score of what? Okay. So now we draw our curve, because now we have where we think the truth is. So what is in the center here? Oh man, you've got to be kidding me. Hold on, guys. Yes. The center is 0.3, isn't it? Okay. This should be fun. Let's see if that did it enough. Yes. So this is 0.30. This is down here at negative 2.31, isn't it? So remember what I said? The z-score, the test statistic, is the line of demarcation. The p-value is the area, isn't it? So we want to know what area is there so we can compare it to where we think the line should be. Does that make sense to everybody? So we've got to figure out why down below that. What did Ha say? Less than, didn't it? So less than would be everything shaded here. So our p-value, honest to goodness, our p-value is going to be this area. It is a proportion, or it is a percentage, isn't it? It is a percentage. What percent, what is the probability, right, of it being down there? That's what we compare it to. So let's find our p-value. To find our p-value by hand, we know that is going to be what? Isn't it a normal CDF? Whenever we draw a normal curve and we find shading on it, we find the area of the shading, that is a normal CDF problem. Lower limit is like negative 10,000 to negative 2.31 to what? What's the mean? 0.3. And what was the standard deviation? Did we find the standard deviation? 0.3 times 0.7 divided by 300, take the square root of it, right?
0.026.
So 0.026. That would be this part of it, wouldn't it? This is that, right? This is our HO, correct? This is our Z. And we should get something. What do we get? What is our p-value? I don't know why I put negative 2.31 there either. I'm sorry, negative 2.268. Excuse me.
I was so confused for a second. I was like, where's
2.268. Sorry. Okay. So it's not going to be very big, is it?
mine still says 0.
Should we use 0.24 as the upper, since the main is 0.3? I think that's what's
Oh, wait a minute. We've got a z-score, don't we? We've got a z-score. Where did I make my mistake, guys? Z-score. If we have a z-score, what should my mean and my standard deviation be? 0. So this should not be, if we're drawing our picture and we're using if we're drawing our picture here and we're using a z-score of negative 2.268, then what should be here? 0, shouldn't it? So we ought to write n 0, 1. Okay, so negative 2.268, 0, 1, right? So we got to be careful with this. And Riley is correct, isn't he? If we were going to use the mean and the standard deviation we'd have to use 0.24. If we're going to use the standard deviation here, so mean is 0, standard deviation is 1. I got 0.004. Is that what you got? No, hold on. I think I entered it wrong. Second vars. I think I forgot. Yeah, that's it. Negative 2.268.
0.117.
Yeah, 0.117. 0.01.
Yes, sorry.
Yes, no, that's okay. So this is approximately 0.01. Now, if we had to make a decision based on this, how would we make the decision? What would we compare? We compare our p-value, which is 0.01, to our alpha level, which I believe we said was 0.05, didn't we? Significance level? Is it bigger or less than? It is low, isn't it? So what do we do? If the p is low, so this would have us reject H naught, meaning there is significant evidence to support HA, right? Which is that what? That the percent, yeah. The true proportion of
Numbers that begin with 1.
first significant digits being 1, right? Is less than 30%, right? We didn't write a P, so it makes it harder to write the statement, but you get the idea. Let's actually go and do another one. It's claimed that 54% of lost remote controls are stuck between sofa cushions. This is a fun statistic, isn't it? Somebody probably paid money for this to be an actual thing. It says, a reporter tests this claim by checking a simple random sample of 500 people who lost their remote controls, and 280 of them reported finding the remote controls between the sofa cushions. Please check it gave you the HO and the HA. So HO would be what? P is what?
Equal to 5.
0.54, right? 54%? Because that's what we think is the truth. And what are we checking to see?
That it's not equal to.
That it's not equal. Why not equal?
Because it can be more or less.
Yeah. He's testing this claim. Since it didn't tell you, he's trying to see if it's more or less. We just do not equal to. So go ahead and write your conditions check. Walker, what are you messing with on there?
Sorry, I was looking at my grades.
Okay. Get off those and focus here. So check your conditions, please.
Is that RIN?
Yes. That would be RAN. Okay? So far, so good? We can assume it's approximately normal. Everybody got RAN? Okay, so now it says calculate the test statistic. So let's calculate our test statistic here. It's something other than angry red. So that would be a z-score, wouldn't it? So we need to find p hat. So what is p hat?
280 over 500,
Yep, we've got 280 people out of 500.
which is 0.56.
So we have 0.56 minus 0.54, right? And divided by 0.54, 0.46 over 500. All right, guys. Can I tell you where people make the biggest mistake in these problems? It's right here. In multiple choice, they're going to give you a choice. They're going to write them out like this, only you'll get 0.54, 0.46 divided by 500. They'll also give you 0.56 times 0.44. They'll give you the p hat in the bottom also. You got to know, you know how I remember it? Whatever you use to check conditions is what goes down there. And you use p to check conditions, don't you? Not p hat. All right. So what did we get for a value here? Did you get about 0.9?
Yeah.
All right, guys. you should be able to tell after a while. Think about this. This is the number of standard deviations, right? If we're only looking at a significance level of 5% on either end, or 2.5% on either end, right, with a significant level of 5, that's more than 2 standard deviations, isn't it? This is not even 1 standard deviation. Do you think we're going to fail to reject? No, probably not, right? Or well, we are going to fail to reject. Do you think we're going to actually reject? No, because it's not out here, is it? The P is not going to be low, is it? Do you see how you can kind of, if you've got less than 1 standard deviation, that's a lot of area, isn't it? Which means it's going to be a really high p-value. Do you see how you can kind of look at the number of standard deviations and kind of tell? You can make a reasonable educated guess of what's going on. So let's actually draw our curve now and figure this out. So when I draw this curve, I need to find what? I've got my p-value, but I need to find, well, actually I don't have my p-value, I have my z-score. So my z-score is what? 0.9 is here, but what did we know about our HA? HA is what? Not equal to, so it's two-tailed. So negative 0.9 as well, right? Now I can only draw this if I put what right in the very middle? 0. And remember we put our n as 0, 1 here so that we know this is a z-score. So we've got a two-tail, don't we? So you got 2 choices when you do this. You can either do normal CDF of the middle between the 2 and then subtract it from 1, or you can do one end and multiply by 2. That's what I suggest. So we're going to find a p-value, which is going to be 2 times normal CDF. Which end do you want to do? Doesn't matter to me. Okay. So lower is 0.9, upper is like 1,000, 0 and 1. So we're going to get 2 times whatever that is. So run your normal CDF and tell me what you get. And then multiply it by 2 and tell me what you get.
How many decimal places do you want?
Just 3 or 2. 2 or 3 is fine. So 0.368 is correct. So I want you to think about this. Is this p-value pretty high? Yeah, that's a lot of area under the curve, isn't it?
Yeah.
Does that put it out in the unusual range? Nah. Unusual range would be way, 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 way out here, wouldn't it? Wouldn't that be where we would think it would be if it was going to be unusual, just a little bit? It's well in front of that. So are we going to reject? This p is not low, is it? So we would fail to reject in this case. Is that making sense? So now it says interpret. Interpret this p-value. This is that ugly interpretation, assuming what? Assuming that p%, so what was p?
54.
So assuming that 54% of lost remotes are where?
Couch cushions.
Yep. Stuck between couch cushions, the probability of getting results as extreme or more so than p hat, which is what? 0.56, right? Simply by chance is what? What is the probability did we find for getting p hat of 56%? 0.368, yes, 0.368. All right. So now, we know how to find the z-score and the test statistic. Now, that's a bunch of work, isn't it? So guess what? Calculator will do it for you. You can run a one-prop z-test. Now, your work is oftentimes plugging into the things by hand. Just like we did with the confidence interval, we plugged it into the stuff by hand and then actually used our calculator to find all the numbers. So go into your calculator under Stats Test. Stat Test. And what do you see?
The one prop Z test.
One prop z-test is number 5 down here. So it's going to ask us for a p-naught. What is our p-naught going to be?
0.54.
Yeah. So we want to do one prop z-test, right? So let's do this for our remote control. Our p-naught is 0.54. It wants an x and an n. What was our x? What was our n? How many remote samples did we pull?
500.
How many of them did actually were between couch cushions? That would be our x. Okay? We want to pick what? Notice you got 3 options. Not equal to, less than, or greater than. So not equal to p naught. All right, so let's put in our 0.54. Let's put in our 280 and our 500. Not equal to. And we want to calculate. Now notice it'll draw it for you too, won't it? Let's just hit calculate this time. Calculate. Look what it's going to give you. It gave me a z-score. What was our z-score? 0.897, right? And what was our p-value? 0.3706970. That's still pretty much what we got, wasn't it? It's very close to what we got. So we can do this by hand. It's going to give us a p-hat and an n. So all of this can be done using your calculator as well. Now, if you do it by hand, that's automatically showing your work. But you got to remember which formula to use, etc. And for speed's sake, doing these, it's easier. Now, why do I insist you do it by hand? Because that's how it's going to show up on the multiple choice, right? You got to know where everything goes in those. So let's make a decision. Our p-value, which is 0.37, is what? Greater than or less than our... It's greater than, isn't it? Our significance level. What was our significance level? Did they give us one?
I don't think so.
So what do we automatically default to?
0.45.
Yep, 0.055%, which is our alpha level. So we what? Is the P low?
No.
So we don't reject, do we? We what? What's the phrase? So we
fail to reject.
we fail to reject H naught. There is not, because remember, you have to talk about H naught, and then you have to talk about HA, don't you? So if we fail to reject H naught, then what does that say about HA?
There's not evidence to
Yeah.
support HA.
There is not evidence to support HA, which is what?
P not equal to
That the true proportion of TV remotes stuck in couch cushions is different from 54%, right? This is how you say not equal to P naught, okay? Is different from. Because that's really what we're checking, isn't it? Is it 0.54 or is it not 0.54? Well, the fact that they're 56%, that's not very different from 0.54, is it? So obviously that's going to make it pretty close. which means it's not going to be far enough away or weird enough for us to say, well, 54% must not be right. Do you get it? Okay. So let's keep multiple choice. Do you see what I mean about the... All right, so let's look at day 6. Conducting a hypothesis test. We did proportions. Now we're going to do what? Means. So now we're going to do means. Are we fixing to go to lunch? Okay, so let's just go ahead and start talking about the phantom. We already know what? How to check our assumptions. So how do we define the parameter this time? What is the parameter going to be this time? Mu as the true means something in context, right? So H naught, ho is going to be, instead of P equals the claim value, it's going to be what now? Mu equals the claim value. Or mu is less than, greater than, or not equal to. All right. Random and independence are the same, aren't they? RIN, the only thing different between proportions and means is normal. So what do we check for normal? N has to be what? Yep, greater than or equal to 30 for CLT, or we have to check that the data is from a normal population. If the population is normal, then you cannot pick a non-normal sample out of it. Once it's normal, it's normal. Does that make sense? Or we draw a what? A graph, and what kind of graph? Box plot, and it shows no obvious what? Yep, no obvious skew or outliers. Outliers. And we're gonna, that graph is always gonna be, for us, it's gonna be a box plot, isn't it? Okay. N, what are we running as N this time? Instead of a 1 prop Z test, we're running a 1 sample T test. Just like we did a 1 prop Z int and a 1 sample T int, we're now doing a 1 prop Z test, 1 sample T test. Here we go. All right, so T, test statistic instead of Z, because Z is associated, of course, with proportions. We've got T, which is, of course, associated with means. We have a T score instead of a Z score, right? So what's the only difference here? Well, of course, the standard deviation is different, right? But we know that formula for adjusting for a sample, correct? Same standard deviation we've been using. And of course, you've got X bar and mu naught. All right, and the p-value, again, to find the p-value, is going to be, instead of being a normal CDF, because this is a normal CDF is only used for your Z scores, right? Since this is a T score, we use T-CDF, which we've done before. And don't forget, you've got your lower, your upper, and your degrees of freedom. And notice on here, notice your test on your calculator is a T-test. All right? It's just labeled as a T-test. Just like the other was labeled as a T-int, this is a T-test. Okay. And M, of course, we're going to make a graph, the T distribution with the accompanying degrees of freedom, the T and the p-value, and then make a decision based on the significance, the alpha level, correct? Just like the end requirements are just like for a Z score and a P appearance test, all right? So let's do one. We've got the light volt right here. Lovely light volt. One of many electric cars increasing in popularity advertises a battery life of 1,500 miles before charging is necessary. All right. A researcher for competitor believes this claim is much too high. Believes the claim is, that right there is going to tell you what you're scoring again. It's too high. So we're trying to prove what? That it's actually what? No. That it's actually less than, right? If he thinks it's too high, we're trying to prove that it's actually less than, right? All right. So what is our parameter? What is mu here? The true what?
True battery life.
Yeah, true mean.
The light bulb.
Battery life in miles of what?
The light bulb.
An electric car. It's not just the light bulb, it's one of many electric cars, right? It just gave you a light bulb. All right, so what are my hypotheses? We've got ho and ha. So what do we think ho is? We think mu is what? What does it advertise?
That it's equal to 1,500 miles.
So 1,500 miles is the claim. And they claim that's too high, so they claim that that is less than 1,500 miles.
That's good. That's pretty fast. Yeah, that's good.
How's that?
That's good.
All right. So, now let's talk assumptions. What are my assumptions? Random. Okay, so for random, what did it say? Yep, of 32 electric cars, independent. We can what?
Assume that there are at least 301 electric cars.
Yep, assume more than 320 electric cars in the population, right? And normal. How am I going to prove normal?
It's great. The sample is greater than 30.
It's greater than 30. So about normal by CLT, right? Okay. So we're running a one sample what? Yep, one sample t-test. Make sure you write test, not interval. Now we need to find our t-score, don't we? So t, x bar minus mu over s sub x over the square root of n, correct? X bar was what? Volts need charging after what?
1,095.
1,095. So 1,095 minus 1,500, right? Does everybody understand where the 1,095 came from? It said on average, volts need charging after 1,095 miles with a standard deviation of?
357.
So this puts 357 here, divided by the square root of how many samples?
32.
32. So that gives us a t-score of approximately negative 6.4. All right, so I want you to use your common sense and tell me, is that a lot of standard deviations away from the mean?
Yes.
So do we expect to reject or fail to reject?
Reject.
We expect to reject, don't we? It's going to be a teeny, teeny, tiny little bit of area out on the end, isn't it? So we're expecting a p-value really, really small, aren't we? Okay, so let's find our p-value then. Do you see how you can look at that score right there and say, all right, there's a lot of standard deviations, so it's going to be really teeny tiny areas, so we expect a really small p-value, therefore we expect to reject. Okay? So that's the type of innate statistical knowledge. So p-value, instead of using normal CDF, what are we using? T CDF. Why can we not use normal? Because it's not a z-score. We only use normal with a z-score. This is a t value, isn't it? So we use t CDF. Do you know where t CDF lives? Just below. Yeah. Second bar, right? Right below t PDF, we've got t CDF. It's giving us, oh, hey, maybe we ought to draw this curve first. or maybe we can look at this. Is this going to be, what are we using here? Shouldn't we draw a curve? This is going to be 0. This is going to be negative 6.4. We're looking for less than, aren't we? You see why I would draw that first? Because that's going to tell me lower bound and upper bound, isn't it? So lower bound is really big, small negative number. Upper bound is what? Negative 6.4. And degrees of freedom? 31. And you should note that somewhere. Degrees of freedom, 31. You should always put that in. All right. We're going to hit paste, enter. We get 1 point. You'd be surprised at this, guys. We get a p-value. Do you know how many people write 1.98 and stop there? And then make a decision based on 1.98. Number one, could this value ever be above 1? Why not? Because it's the area under the curve, isn't it? And so it can't be bigger than 1. So 1.98, it's 1.98 times 10 to the negative 7. That is a really small number. If that p is low, and it is, we are going to reject the hoe. So let's make a decision. Since p is 1.98 times 10 to the negative 7, that is far less than 0.05, right? Which is our what? Alpha level? We what? We reject H naught. Therefore, there is sufficient evidence to support what? This is where you go back to your mu. That the support that the true mean battery life in miles, or in hours, in miles, of electric cars is what? What is HA?
Less than
Yeah.
1,500.
Is less than 1,500 miles. Okay. Do you see how this brings your mu and your HA into play? Mu and HA are, when you write them, go into your form. All right. What's the difference between this one and the last one? Yeah, it's a table. Now, I'm going to be nice to you, and you know what you'd have to do here. What's the problem? Simple random sample of what? 20 sodas, which means we don't have CLT satisfied, do we? So we would have to we'd have to put it in our list and draw a box plot. So for normal, let's just go down here and say we did. We get this. And this is 31.45. This is 31.775. This is 31.975. This is 32.15. And this is 32.65. What do you notice about this guy? No obvious skew or outliers. So approximately normal. Okay, we're going to assume the rest of the assumptions get met. Let's write our mu and our H naught and HA. What is mu? The true mean what? Whether the actual amount given the soda is what? Yeah, soda dispenser. So it's going to be the true mean amount of soda dispensed. in ounces, right? Okay, so what do they think the true mean is?
32.
Yep. See, that line represents 32 ounces. Fill a cup to a line. So 32 ounces. There is concern whether the soda dispenser is working properly. In other words, whether it is actually giving the amount of soda it is supposed to. So what does that imply?
Not equal, not equal.
Good. Do you see how the hypothesis is like the most important thing? Because that tells you how you compare and how your curve is drawn and whether it's a one-tail or a two-tail test, etc., right? Okay, so let's go ahead and run our what? One sample t-test, right? So let's find our t. So to find our t, first thing we need to know is we need to know our degrees of freedom. What's our degrees of freedom going to be?
31.
How many samples did we have?
Oh wait, never mind. Sorry, it's 19.
Yeah, we need to find x, or we need to find mu and everything, don't we? So this is going to be 19, isn't it? Degrees of freedom is 19. And what is x bar? What was the experimental that they gave? Read it. Do we even know?
No.
But we put all our numbers in, didn't we? If we put all our numbers in, what could we run? One variable statistics. If we had done that, it would have given me a mu of 31.98. And it would have given me a standard deviation of, oh, wait a minute. Hey, what did it say? They gave us the standard deviation, 0.075. Cool. So that makes it easy. And we know mu is 32, right? So let's plug this in. This becomes 31.98 minus 32 divided by 0.075 divided by the square root of 20, doesn't it? All right. I know we're going to run out of time here. So let's just go ahead and, we've got like 4 minutes left. This is going to give us negative 1.19. All right, so realistically speaking, do you expect to reject or fail to reject?
Fail to reject.
Not a very big standard deviation, is it? A little more than one? And this is a one-tail or a two-tail?
Two-tail.
Which means it's really going to be a lot of area, isn't it? So let's draw our picture. And then let's find our p-value. So if I draw my picture, and this is 0, what am I going to draw on here?
Negative 1.19. 1.19.
And where do I shade?
To the left and to the right.
Yep, shading out here. And this is N01, isn't it? Are we good with this? So to find our TCDF, this will be our p-value, won't it? We're going to have, this is only going to give us what? One end, isn't it? So to find the p-value, what do we do? 2 times that. So let's be careful and make sure we write that in. It's going to be twice TCDF, where we go from 1.19 to one really big number, and degree of freedom is 19, isn't it? All right. So go find TCDF and enter your stuff in.
What's lower? Negative big number?
Yeah, you can do it that way. Negative big number, negative 1.19, 19, or you can do 1.19 to really big number, 19.
Yep.
Doesn't matter to me. One end or the other. What do you end up with as a p-value? Yep, 0.24 is 100% correct. So now I want you to make a decision. I want you to write it out. What is alpha level? What is our significance level? Does it say?
No.
So what are we using it as?
Oh, it does. It says 5%.
Ah, is there evidence at the 5% level? So 0. If you write out p-value and alpha level, then you can just compare them over here. In other words, you can just say 0.24 is what?
Greater than 5%.
So, talk about H naught first. Are you going to reject or fail to reject? Therefore, there is or there is not?
There is not.
Good. Failing is not, isn't it? Not sufficient. You know how else you could say that? It's not convincing evidence. There's not sufficient evidence to support what? You can say HA, but you better finish with what that means in context. The soda machine is what?
Is dispensing 32 ounces. I put it up. I can't remember.
Something, what?
Something
Other than, yep, 32 ounces of soda. Something different from, other than what we got, okay? So are you guys good with this? Okay, you've got day 5 and day 4 and day 5 and day 6. I think day 5 there isn't homework, it's just day 4 and day 6. What you will be doing is day 5 is timed writing, which we'll do next time. But the big thing is you've got at least 2 of these with proportions to work all the way through and 2 with means to work all the way through, right? And then some free response or some multiple choice questions. It's good. The more you practice writing these out, the better you're going to get at them. Okay?